Hi, in this video we're going to learn how to deal with higher order differential equations. As it turns out, what we've already learned about second order differential equations is quite easy to extend to a case where we have nth order differential equation. So let's just say that this is the differential equation we need to deal with. So this is nth order differential equations with constant coefficients and constant term. How do we solve it? Okay, as always, we need to distinguish between particular integral and complementary function. So let's start with particular integral. And keep it in mind that, of course, when we solve this, we use trial solutions, and we always want to start by trying the simplest one. Okay, so if I want to find particular integral in this case, I can use what we've already learned. So let's assume that an is different than 0. What would we choose for our solution? Well, the best choice at the beginning is a constant, right? If we've got a constant, y is a constant, then of course each next consecutive derivative is equal to 0. Okay, and look, then it means that all those components over here are equal to 0. So all we've got is that an times y and y equals to k equals to b, right? And out of that, we get that k equals to b over an, and we get that the particular integral, in this case, is simply equal to b over an. But right away, we see the necessity of this assumption that an is actually different from 0. Okay, so what do we do if an is equal to 0, however, an minus 1 is different from 0? Well, we know that this solution is no longer going to work, right? So we choose the second easiest solution. We choose k times t, which means that y prime, in this case, is k, while y is, as any other derivative, is equal to 0. Okay, and again, look, now with an equal to 0, this part is gone. With all those derivatives being equal to 0, this part is gone, right? So the only thing we've got is that y prime equals to k, right? So we've got a to k equals to b, right? Because we substitute for y prime, sorry, not a2, an minus 1. And of course, out of this, we calculate that k is equal to b over an minus 1. However, y is equal to kt, which means that the particular integral in this case is equal to b over an minus 1 times t. Okay, so what do we do if now both an and an minus 1 are 0? Okay, an equals to an minus 1, they are both equal to 0. However, an minus 2 is different than 0. Okay, again, we know that this solution is no longer going to work. So we need to try slightly more complicated one, right? So we choose that y is kt squared. This means that y prime is 2kt, while yb's is equal to 2k. This is a constant, which means that each next consecutive derivative is going to be equal to 0, right? So, again, we see that all the components over here are equal to 0, except for the one associated with the second derivative, right? Those are gone because derivatives are equal to 0, and those two are gone by assumption, right? So, now we get that a n minus 2 times, of course, yb's, so 2k, is equal to b. And look, out of this right away, we can calculate that k is equal to b over 2a n minus 2. And this implies that the particular integral, if we substitute for k, is equal to b over 2a n minus 2d squared. Okay, and I hope this gives you some sense of what should we do in each case. Now, if we move further, that an equals to an minus 1 equals to an minus 2 equals to 0, and an minus 3 is different than 0, we know that this solution is no longer going to work, right? So we need to try something even more complicated. So, kt to the power of 3. In this case, y prime is 3kt squared, yb's is 6kt, and third derivative is 6k, while every next derivative is equal to 0. Okay, and look, again, we are just going to end up with one component. This component is going to look as a n minus 3 times 6k equals to b. Out of this, we can easily calculate that k is equal to b over 6a n minus 3, and this means that particular integral is equal to b over 6a n minus 3 times t cubed. Okay, I hope you see the pattern, but I'm actually going somewhere with this. So bear with me for one more case. Let's now go just one step further. If an minus 1, an minus 2, and an minus 3 are all equal to 0, and an minus 4 is different than 0, what should we do? Again, we go one step up. We need to try more complicated functions. So we've got k times t to the power of 4, y prime is equal to 4k t to the power of 3, yb's is equal to 12k t squared, third derivative is equal to 24k t, fourth derivative is equal to 24k, and every other derivative, so fifth derivative until nth derivative, are all equal to 0. Okay, what should we do with this? Okay, like the trick is very easy. Again, all the components are gone except for an minus 4 times 24k equals to b. Out of this we get that k is equal to b over 24 an minus 4, which means that particular integral is equal to b over 24 an minus 4 t to the power of 4. Okay, look, I hope you can see that there is a pattern to it, but actually the pattern here is so clear that we can actually create a formula for any case where we have some missing components. So some number of an parameters is actually missing. Okay, so let's start from the beginning. Look, how many components in this equation are missing? 0, right? And let's notice one simple thing. Here, I could say that I'm multiplying this expression also by t. However, this t, oh, I'm sorry, not here, it's in here, by t, but this t is in power of 0, which is equal to 1, right? Now, over here, I can see also that I've got a number 1. That changes nothing. Okay, let's see what happens over here. Over here, I've got t to the power of 1, right? And I could say that here I've got 1. Okay, and from this moment on, we should start seeing some pattern. Okay, now, when we go to the case number 3, what do we have? We have 2 over here, 2 over here, 2 over here, right? Then what happens? We've got 3 over here and 3 over here. However, we've got 6 over here, right? And finally, in the fourth one, we've got 4 over here, 4 over here, and 24 over here. How can we make sense out of it? Well, look, definitely there's a connection between those two, right? Those two are always the same, right? Here we've got an minus 1, t to the power of 1. Here we've got an minus 0, t to the power of 0, right? Then we've got an minus 2, t to the power of 2, an minus 3, t to the power of 3, an minus 4, t to the power of 4. Okay, so this is clear. This is definitely some clear pattern that is showing us what is going to happen. But what about those? Look, those are also changing. However, they are changing in a very weird way. This, first we've got 1, then there's 1, then there's 2, 6, 24. Where have we seen numbers like this? And how those numbers could be connected to numbers 0, 1, 2, 3, 4? And the answer here is very simple. Those are factorials. Because look, this number is equal to factorial of 0, which we assume is 1. This is factorial of 1, right? Now, 2 that we see over here is a factorial of 2, right? This is 1 times 2. Now, 6 that we see over here is a factorial of 3. This is 1 times 2 times 3. And 24, I hope you can guess, is simply factorial of 4. This is 1 times 2 times 3 times 4. And look, actually, this is giving us a formula that can show us what will be the particular integral in a specific case. Okay, so look, we're starting like this. So given higher order differential equation with constant coefficient and constant term, now for first I missing expressions where we mean the function, so y, and its consecutive QT derivatives. We get that yp, so particular integral, is equal to what? It's equal to b over here, I factorial times an minus e times t to the power of e, where e in this case is not, I is not in this case an imaginary number. It's just, indexing our missing expressions. So look, you can clearly see that if, for example, we would have a differential equation that looks like this, let's just say, for simplicity, y7 3 y7 eighth derivative of y plus 3y times 7th derivative equals to 2. What is going to be the particular integral in this case? Look, we can read it from the fact that we've got 7th derivative. So, how many elements do we have missing? Look, we're missing the function, first derivative, second, third, fourth, fifth, and sixth. Right? So we are missing the function at 0 and 1, 2, 3, 4, 5, 6 derivative. We are missing the 7th element. And look, in this case, yp, of course, is equal to b times 7 factorial times an minus I, which happens to be 3 times t to the power of 7. Okay, and look, you don't need to know this formula by heart, of course. However, what I wanted to put your attention to is that there is a pattern, and this pattern gives us this formula for particular integral, assuming that we've only got one constant term. Of course, if it happens to be that we've got more than one term, what we need to do is to move to the method of undetermined coefficients. Okay, so now we know everything about finding a particular integral for higher order differential equations with constant coefficients and constant term. So now let's move to complementary function. Again, everything that we've learned about second differential equation is enough to extrapolate these results, to expand them to more complicated cases. Okay, but let me just finish erasing the blackboard. And let's remind ourselves couple of things. Okay, first, if I want to find complementary function, I need to just solve reduced equation, right? This one. Okay, I hope everybody remembers that the trial solution that we used was in the form AERT, right? Where we of course know that this solution is different than 0. This component must be different than 0. Okay, and look, what's going to happen if I'm going to substitute this solution for y, and I'm going to be taking consecutive derivatives? Well, we remember that this r, each time I'm taking derivative, the only thing that is actually changing is that more and more r's, so in multiplicative terms, are appearing in front, right? So we are going to the power, so the power of r is simply going to increase, right? So, if I'm going to substitute those results over here, they all going to have one common component, right? A, E, R, T. However, inside, each of them will be characterized by different coefficient, right? And a different power of r. So we will have first r to the power of n plus a1 r to the power n minus 1 plus a2 r to the power n minus 2 plus until a n minus 1 times r plus a n, and this is equal to 0. And look, because we know that this expression cannot be possibly equal to 0, what we are getting as a result over here is a characteristic equation, just like we had previously. Okay, and look, this characteristic equation can have up to n different characteristic roots. So look, once we find all those roots, we've got a complementary function. How is it going to look? Look, our complementary function is going to be a1 times e to the power r1t plus a2 times e to the power r2t plus a3 times e to the power r3t plus n until a n e to the power r n t, which we of course can simplify using some notation, and we get that for I equal to 1 up to n, we've got a I e to the power r I t. Of course, remember, I in this context is not an imaginary number, it's just an index. Okay, so look, as you see, there is not much more to it. Of course, solving this characteristic equation is going to be far more involved than actually doing just a case for of quadratic equation, which we know how to deal with very, very well. However, the idea behind this is exactly the same. And of course, in the next video, we are going to actually learn how to deal with this without finding the actual roots, because sometimes this is not that important. Okay, especially in those more complicated cases. Okay, so we know what happened, how we deal with the case of complementary function. However, there are some things we should definitely take into consideration. Look, I kind of implicitly assume that those roots are distinct real roots. However, this doesn't need to be the case. So, let's put a little but on all of what we said thus far. Because we need to take into consideration what happens if, for example, we have repeated real roots. So, anytime we have repeated real roots, for example, let's just say that we have solved this equation, this differential, this characteristic equation, and we found that R3 is exactly the same as R6 and exactly the same as R7. Let's just say that all other roots are completely different, right? What should we do with these three? We use exactly the same trick we used with repeated roots before. Look, so in our complementary function, that would start with some a1 e to the power r1t plus a2 e to the power r1t. We would get to the r3, and we would write a3 e to the power rt, right? And that would be R3. Then plus, we would have some more components, and then we would get to R6. We would have A6, but this R is the same as this one. What do we add? We add T. So we would have T, E, R, 3, T, right? Because those are all the same. And then we would have plus A7, T squared, even bigger power, because here we have ER3T, plus add some other components of the complementary function. Okay, so now we know what to do when we've got repeated real roots. All we've got to do is for each repeated root, like here it's 3 times, first we put it in the regular form, then we add 1t, then we add t squared, right? Now, So probably the next thing we should deal with is what do we do anytime we have repeated complex roots. For example, okay, so look, let's just say that now we've got a case like this. R1, R3 and R4 are exactly the same as R7 and R10, and those are exactly the same. Oh my god, no. R3 and R4. Let's just say now we're gonna have R7 and R8 and R10 and R11 or R9 and R10. Okay? And they are all in the complex root form. What should we do in this case? Look, again, the solution is the same as before. The solution is exactly the same as before. We add t. So look, we would have some components of the complementary function, and then we get to, to those two, R3, R4. What would we use here? E to the power ht times a, that would be 3 cosine vt plus a4 sine vt. Okay, so that would be the first expression, right? So we've dealt with the first two. Okay, so what do we do next? Then we've got some other roots, and then we go back to those roots. The trick is to simply rewrite the same expression and multiply it by t as before. So we will have a8 cosine vt plus a7 and a8 sine vt. And then the next would be, as you can probably guess, e to the power ht times t squared. Of course, times a9 cosine vt plus a10 sine vt and plus other components of this complementary function. So basic trick here is to add those t's with bigger and bigger power to each repeated set of conjugate complex roots. Okay, so knowing all this, let's just deal with one example to make sure that we understand how to apply it to the cases we might actually encounter in exercises or in economic problems we're going to be dealing with. Okay, so let's just say that equation that we've got goes like this. Y to the power 4 plus 6. Fourth derivative of y times 6. Third derivative of y plus 14 base plus 16 y prime plus 8 y equals to 24. Okay, as usual, let's start with particular integral, which is extremely easy in this case. We know that an in this case is different than 0, so particular integral is just equal to b over an. In our case, that would be 1, 2, 3, 4. So A4 is equal to 24 over 8, which is 3. So we've got a constant equilibrium. Now, for this equation, we can easily see that the characteristic equation is going to be r to the power of 4 plus 6r cubed plus 14r squared plus 16r plus 8, and this must be equal to 0. Of course, solving this is very, very problematic. It took me quite a long time, and I'm not gonna be doing this with you here, especially that in the next video we're gonna learn how we can assess convergence and stability of equilibrium without actually needing to calculate all of this when we have rather complex differential equations. But if we solve this, it would turn out that we can rewrite this expression to r plus 2 times r plus 2 times r squared plus 2r plus 2 equals to 0. Okay, and look, what do we get? Over here, we see that we've got two repeated roots. So r1, r2, both are equal to 2. Over here, however, we would get pair of conjugate complex roots of the form like this. Okay, now we need to build the complementary function. So what we're going to have, okay, first we need to deal with repeated real roots. Right? So we will have that this is a1 e to the power of r. So let's those two call just r. Okay, or r1, right? T. Now plus we have the same root, so we need to add t. So we've got a2 t e to the power r1 t. Oh, and of course here should be -2. So, yeah. Okay, let's just substitute the outcomes. Okay, -2 and -2 over here. Okay, then, now we've dealt with repeated real root, and now we move over here. So, to deal with case of the complex, if we've got a complex root over here, but not repeating, we will have just that this is e to the power of h, which is equal to -1 times t, times a3 sine v is just 1, so, cosine t plus a4 sine t. And this is it. We can, okay, let's just say to put everything together, of course we should combine complementary function with particular integral, and it turns out that the time path of y is equal to a1 e to the power -2t plus a2 e to the power a2t e to the power -2t plus e to the power -t times a3 cosine t plus a4 sine t plus the only thing missing is particular integral 3. Okay, so at this moment you have the tools to deal with differential equations with various degrees of complexity. And you know in principle how to deal with n-order differential equations with constant coefficients. And in some cases even even know how to do it with variable term, not only the constant term, because you know how to use method of undetermined coefficients. However, look, already we've encountered this. This, what you see over here is a characteristic equation where the polynomial is of the degree 4. So this is a very, very complex thing to solve. However, look, very often we're not interested in where this equation can be solved. Look, what do we want to know? We want to know whether there is a convergence or divergence. When there is a convergence, well, convergence happens if all the roots are negative, if all the real roots are negative, and the real part of a complex root, so h, is also negative. So look here, because all the real parts of the roots are negative, we know that there's going to be convergence over here. However, maybe it would be better if we could solve this without solving, which will require from us a lot of work. As it turns out, it is possible. And we're going to use the root theorem to show, to deal with cases like that. And this is going to be a topic of our next video. Okay, thank you for your attention, and we'll see you in the next video.